Okay, so I have done a lot of engineering work across computer graphics and gaming, aerospace, and virtual reality. What I'm going to talk about today is systems engineering, which is looking across all the different pieces that make up the elements that are part of a problem and seeing how you can cut out pieces and optimize the different areas. Because this is something that I use across all of my real successes, have had elements of this, where if you divide a problem up the way things are done nowadays, everybody gets their little specialization. You have the person that's going to work to make the best this and the person that's going to work to make the best that, and they're going to be coupled together in some way with an interface. But in many cases, there are built-in inefficiencies from that, where if person A doesn't know that something's different in person B, they're just working through the interface, that's all you get. So this has given us marvelous things. We have the ability to get, just kind of pull levers and have amazing things happen across, different aspects of engineering. But knowing what's actually going on in the different areas can allow you to sidestep a lot of things and get greater efficiency. Like in one of the rocket ships that we built, one of the things was, it was a lunar lander simulator where you have a rocket that just moves over, flies down, and lands in another place. One of the major aspects to that is landing gear. The lunar lander program spent immense amounts of effort building the landing gear for the real lunar lander. And you would have teams of people that work and say, I'm going to build the best damn landing gear the world's ever seen. This is my task, and I'm going to be an excellent engineer and do a great job. But one of the things that we did on one of our vehicles was say, well, what if we just didn't have any landing gear at all? We've got pressure-fed propellant tanks. What if we just put a little bit of rubber on there and just let it kind of thud down on the ground? And it turns out that actually works just fine. You had this entire section of engineering, which was do the landing gear, and instead of getting it better and better, it just completely vanished. So that's one example of kind of looking at the entire problem. If we're trying to do this lunar lander simulation or analog, when we look at a lot more computer science type things, one of my canonical examples now is the virtual reality head-mounted display. And this was a really interesting trip through all the systems that go on making this up. Where a traditional computer game, you can think about it, you've got your computer, and you've got some input going in, maybe a game controller here, and then you've got your output going to a monitor. That's what happens in a game. It's your classic computer science system where you've got inputs, you've got processing, you've got outputs. And this is fundamentally what video games and everything that you do with a computer does. So it's easy to see how people thought that if you want to take a virtual reality headset, you have the same computer, and you plug into a headset over here that's got some things to look through over there, strap on the back, and you have a sensor coming back that's telling you which direction it's pointing, and then it's basically taking the place of the monitor. And it looks like you basically have just jammed two peripherals together into a new device, and that should be able to do what you want. But when you do that initially, it's really disappointing, because what turns out to be all right in terms of responsiveness for traditional gaming is really lacking when you wind up putting it directly on your head. One of the factors that's been, that's an issue for almost all interactive things is the latency, where it doesn't get tested nearly as much as bandwidth, the numbers that people like to tout in advertising. But the delay between the time something happens, like you mash the button on your joystick here, it goes into the computer, and the time you actually see something changing on the screen. The difference from motion of, say, tapping something to the time that actual photons come off of the screen and head towards your face and your eye and are processed. Now, in the old days, if you go back to very old gaming systems like an Atari 2600 or something, these were extremely low latency, under 16 milliseconds, where in many cases you're doing something on your controller, and the raster coming off of the CRT is changing, potentially even on the same line, fractions of a millisecond after when you've done something. But modern computers have an enormous amount of buffers and subsystems between what's happening here and what actually comes out there. In fact, a modern joypad has a more powerful microcontroller than what an old video game system would be, like an Atari 2600. You have more computing power and much more processing going on just in here than what used to be the entire system. So as with any good engineering effort, when you want to improve something, the first thing you have to do is measure it. You have to decide what you want to measure, find out what your process is for measuring it, and then collect some data. So one of the things that even before virtual reality time, there's one metric that was important for gaming was ping time, the latency on a networked game. That's nice because it's a latency that the computer can measure itself. It's how long do you send a packet out, you mark time, send a packet to somewhere, when it comes back in, you record the time, look at the delta, and you can say, this is the latency of my network communication. That's nice and easy, makes for easy optimization of the different things, even though it's a very complex system. With physical things in the real world, it's a lot harder because the computer by itself can't tell you exactly how long, when something happened. All it knows is when it finally came in from the system there, and it knows when it pushed something maybe out to the screen, but probably even there, further back up. So what I would be doing in physical gaming, kind of this end-to-end testing, is I would take a high-speed video camera. Nowadays, everybody's phone can record 120 or 240 hertz, and that's a great thing. But 5, 10 years ago, you had to buy a specialized camera that could record at the higher frame rates. But I would set up all of these cases where I've got the camera recording, I would have the joypad sitting there, and a TV screen there. You get them both in frame, you mash the button with a really sharp impulse, and then wait till something comes on the screen, pull the video off of the camera, and then step through it one frame at a time. And you're like, all right, on frame 27, the button is pushed down. And even there, it gets a little bit mushy as you're looking at, is the button first contact of the button or the time it's fully deformed down? So there's some skew if you're trying to be really accurate about which 4 milliseconds it's on, but you can certainly tell within 10 milliseconds or so very easily. And then you count frames off, you single step, single step, single step, until you wind up seeing something coming out on the screen. Conventional video games, for a number of reasons, have taken some pretty large steps backwards in responsiveness. And this usually gets driven by, gets driven by graphics. I mean, a lot of blame can be laid at my feet for starting a lot of these trends on what people would optimize for. But when you optimize for the image that comes out of the screen, you're optimizing for, in many ways, bandwidth. And all that goes on in the CPU and the graphics processor and all of this stacks up more and more latency, to the point where if you take a modern Xbox game, or PlayStation, not to be partisan about any of that, but a modern console game plugged into a typical user's television set that might be in your living room, and you do this test, it is very common to have over 100 milliseconds of latency from the time that you mash a button to the time when something actually changes on the screen. Now, with a gamepad for a console, that's not that terrible. People that are connoisseurs of gaming or that are competitive gamers will care about all of these small amounts, but especially people that are playing a third-person game where you're controlling the guy running around down on the screen, you lose more in the animation blending between how the character moves around than this, and it's hidden fairly well. If you get into more competitive types of games, like first-person gaming, and you're using a mouse, then it's much more of a problem. But you can make sort of a graph of the value of this response time, where if you have time down here and arbitrary scale of value here, if you have something like a gamepad, you might say the value, say this is 100 milliseconds. You've got, this is okay-ish here, and it goes up and it gets more valuable, but there's a certain point where gamepads in many ways are terrible because you're integrating the position of your thumb over time. This is not a great human user interface way to do things. It's very imprecise. It's amazing to look at what the best players can do with this, but it's fundamentally not a great user interface. If you look at something like a mouse, when you're controlling directly your point of view with that, that's a direct one-to-one correlation. And that has a lot more value where that can go up higher. It probably starts lower when you've got a lot of lag. A laggy mouse feels worse than a laggy game controller, but it can go up, and then it can get to be significantly better with much lower times. And you can get down to tens of milliseconds being a really useful thing. Now, with a head-mounted display, when you've got it on your head, the goal is to make it feel like you're in a virtual world, like you are just looking around and the world is solid and it's just there. If you have an appreciable amount of latency, you can still say it's like, oh, it responds to the way my head is turning. You know, I can turn my head and then it comes over and it looks here. And there's a little bit of value to that, but there's no way you mistake this for saying that I feel like I'm really there. And this is the way virtual reality displays really were for a couple decades, where you would see people write articles that talk about how it's going to change everything and it puts you in a different place. But so much of that was really garbage, where if you tried these actual displays, you would say, I can imagine what this would be like if it was actually good, but that's not what I'm actually experiencing right now. And that sense that you're using your head as a controller, basically, and that's not great, and it can make you really sick quite quickly. You know, when the world does not respond the way your brain expects it to, your brain tends to, you know, one of the theories is your brain thinks you've eaten something poisonous and it's making you see things incorrectly, and you should therefore throw up and purge it out of your system. And this is one of the problems with head-mounted displays, that if your synthetic view of the world is far enough from the way the rest of your body, specifically your vestibular system, thinks it should be, then it can cause you to be sick. Now, it turns out that the value then, there's a number around maybe 20 milliseconds is about what we've decided is the part where it feels pretty much like what it should be, like what reality. There are still things that at 20 milliseconds, there's a few tests you can do, like if you start rattling a head-mounted display on your head, you know, in certain ways, you can tell the difference between 20 and 15 or 10 milliseconds, but you have to be really pretty precise about it. Even people that are inside the industry, I could A/B test, and the difference between 15 and 20, very few of them would be able to tell the difference. So there is a point that's of high value, but it does taper off, you know, fairly well from that. But it's a steep thing somewhere around between 20 and 30 milliseconds, where if you're at 50 milliseconds or more like that, it's just not a good head-mounted display. So the challenge then becomes, how do we take something that might be running at 100 milliseconds and get it all the way down to 20 milliseconds? You know, what are all of the things that contribute? And this is an extremely complicated system. There are so many pieces that are moving, some physically like the actual head-mounted display, but just in terms of systems that go through all of this. You've got this simple model. Here's the computer. I'm plugging in a sensor. I'm pulling the video system out of here. You know, where is all the complexity? And it breaks down into a whole lot of things. So if you start at just the sensor, this was something that surprised me when I first got into aerospace. I thought, well, I'm going to build a guided rocket. The rocket needs to know which way it's pointing. Coming into it as a naive software-only person at that time, I thought, well, surely there's just a sensor you buy that tells you which direction things are pointing, that this has to be a solved problem. And I was really kind of surprised at how it's not that simple. There's no sensor without trade-offs that gives you what you would want for carrying a vehicle around. And virtual reality tracks many of these things, where you can use optical systems with cameras to track things, and you have to worry about occlusions and differing precision the further you get from it, and various other things like that. But the most basic system that all virtual reality devices have now is an inertial measurement unit. And this is very similar. We used IMUs, they're called, in the rocket ships that I built as well. And in fact, when I first started working on virtual reality, I literally went and I took code from my rocket ship and that does the integration, and I copied this over to the PC project and said, well, this does integration in a good way. Because this basic sensor, you take it called, the cheap ones are called MEMS, micro-machined sensors, an inertial measurement unit. So the first virtual reality headset that I start working with, it's got a MEMS sensor there, and it's got a library. You can talk to this, and it will give you back, and you can say, what's my orientation, like my body frame? And it will happily give you a number back. But it turns out that just that sensor alone at that point, even if you measured nothing else, was nearly 100 milliseconds of latency. So just that box that you'd hope is one part of this long chain that ends in the display, even that part was 5 times more than what needed to be there for achieving a really good experience. So if you look inside that MEMS IMU, there's actually potentially 3 different or more different processes. There's the actual sensor Then there's a microcontroller, and then actually even the sensor has a little processing device on there. So the sensor itself, these are these tiny etched sensors that can vibrate at very high rates, and it might be outputting at 50 kilohertz. So you might have just a couple microseconds of time between the times that it could be updating. So how does it go from being a few microseconds of time there down to 100 milliseconds by the time it's gotten to the computer? So this is where you start getting into buffers and filtering. And in this entire chain of things that we're going to go through, there are buffers everywhere. Some of them don't matter much, but some of them really pile up into very large values. It was my belief, looking at this somewhat from the outside as black boxes, that there was an immense amount of buffering and filtering that went on in here, largely based from when these sensors first came out a decade prior. They really weren't very good, so they're very noisy. And when you have a sensor with a lot of noise, to get a clean signal out of it, you just average together 100 or 1,000 values, and you can get, you get better precision by the square root of the number of samples that you wind up putting together. So you can take a crummy sensor and filter it enough to get a pretty good value out of it. Calibration is a whole other large topic that can be gone into. But at some point inside there, they were buffering up a whole lot of it and filtering it to get a number out. From there, it would go into a buffer queue here where this little thing spits out, does some filtering on its own. It spits things out. This microcontroller keeps another buffer queue that it's looking at. And then, on a certain cadence, it communicates over USB. Now, the USB protocol is big all by itself. It's what you connect your keyboards and mice and so on with, but a USB driver is actually hundreds of K of code. It's a significant amount, and there's lots of different modes that it can operate in. There are normally, and this is where the history of the world around it affects some of the system choices, where a better way to correct controllers like this, in theory, over USB would be what's called isochronous mode, where you treat it like a microphone, where it's just continuously streaming and it comes out with very low latency. But instead, these are all hooked up through what's called human interface devices, or HID devices. And the reason for that has nothing to do with technical choices. It has to do with the fact that you can make a generic HID device and not need to get a driver signed by Microsoft to install it on your operating system. So here we are with something, there might be a better way to do this, but for reasons of convenience and technical inertia, these are instead sent out essentially pretending it's a mouse to some degree. Now the rate that goes out is a configurable parameter. You take your basic USB device like a keyboard, and it's usually 125 hertz, so 125 updates a second, 8-ish milliseconds per update. But when you've got an update rate that comes out in fixed times like this, you've got 8 milliseconds or something between that. If you have an impulse, like somebody whacks the side of this sensor just sharply, and it comes out right here. So you've got a motion event that happens there. It might be getting processed in here, but it's not going to be sent out to anything else until it gets to this next time period. So you have a variable and fluctuating amount of latency there. So that can add up to 8 milliseconds right there, even if this was the filtering completely vanished. So you have that instantly going out. You could still have 8 milliseconds of time, or 0 to 8 milliseconds, depending on when an impulse actually happened, before it winds up making its way to the computer. So inside the computer, the PC, say, that of course doesn't go directly to the application. It's going to go into an operating system buffer, and the application might be in a blocking read mode or a polled mode, and there's going to be some number of milliseconds. This turns out this can vary a lot by the operating system. You can get hard real-time operating systems that can respond to external events within a few microseconds. But on Windows, usually it's a couple of milliseconds. It's not too bad. That's not one of the really major contributors to this latency. Then you have an opportunity for your application to read the event and do something with it. We come back to cadences again here. Now, a typical console game, say today, will run at, unfortunately, 30 frames per second. Sort of the higher class of games that care more about latency and responsiveness would run at 60 frames per second. But you might have, even if you take the optimistic point and say 60 frames per second, so you've got this 125 hertz going on for your mouse, and then you've got some slightly asynchronous 60 frames per second. Or if it was 30, it would be much longer. So you come to the point where this event happens, eventually it makes its way to the USB transmit, it gets transmitted over, and there's also a delay just transmitting across the wire if it's a significant amount of information. These are relatively small, so that's not really significant, but if you get into things like video streaming where the bandwidth time can then equal your frame time as a whole nother level of inefficiency that goes, or delay at least, that goes in there. So your event happens here, it gets sent out over USB here, it takes a little while to transfer across the USB, a little while to get through the driver stack, and then eventually the game gets around to its next frame and reads the input. It says, all right, what's actually happened? So already we've piled up 16, 20 milliseconds of delay here, even disregarding the filtering. Then you think, well, the game is going to do something and draw an image, and it's going to go out the video system. But most games today are multi-threaded to increase what they can do. So you can have more things going on. You can have, instead of 10 enemies, you can have 20 or 30 enemies fighting on the screen at the same time. So there's a pipeline where you might have CPU 1 reads the input and does things, but you might have CPU 2 doing the drawing. And these are pipelines so that they're all going on in parallel, so you can sort of be creating 2 frames at one time. Most games are set up at least pipeline with 2. Often we have more processors going on, but not in a strict pipeline. But the separation between game and rendering logic is actually quite common. So it might be your input comes in here, but instead of actually being done at the end of that frame, which generously, again, 16 milliseconds, pessimistically 30 or more, it then turns into a buffer of commands that get forwarded down to the next CPU, which runs for another frame. And then, instead of being done here, at this point, it's actually often handed off to the GPU. So now you've got your graphics accelerator, which, if a game is maxing everything out and taking full advantage of the system, is going to be carefully tuned to use almost the entire frame for its actual processing. So it then goes through all the graphics processor, but even then, it's not immediately displayed. We come to buffers again. There are buffers in each of these places. Usually, this is fixed to not be able to buffer things up. If something was architected poorly, it might be, but the amount that the graphics processor can soak up can sometimes be very large. And this gets influenced by things like benchmarking trends. A benchmark is almost always reported as frames per second, how fast this could render flat out. They're not paying any attention to latency at all. So it's in a graphics vendor's best interest to have enormous buffers, because if a buffer ever runs dry, then the graphics processor says, I have nothing to do, I'm just going to idle. And hardware vendors hate that. They want their systems to be occupied all the time, even if it means winding up with latency that you don't want there. So this can sometimes be much worse. But if we're assuming that you've gone to the trouble of there's ways you could force the graphics processor to not buffer any more up, but you can still have a whole nother frame there. But even there, it's not ready to go out, because then it's put into the swap chain to be presented to the video driver, to be presented to the actual video screen. And that setup, it might be double buffered or triple buffered, and there's reasons why you might do that to make things smoother, but they all wind up harming latency. So you might have multiple additional frames where it's done, but it's sitting in a queue waiting to be displayed. And then finally, when it's actually ready to go out the back of your computer to the monitor, over the wires going up there, it starts scanning out, not all at once, but it scans out one line at a time. You've got your screen, and just like CRTs from 50 years ago, it starts at the top and scans the lines out one at a time. This does mean, this is not obvious to people initially necessarily, but the top of your screen comes out 15, 16 milliseconds earlier than the bottom of your screen. In the old days, when you had CRTs, you could actually, like if you had a slow motion camera, or you would see the beat frequencies of the strobing that happened when you were recording at one close frequency and it was displaying at the other one. But if you take a slow motion camera, you could actually see it drawing out and lighting up as it goes and then fading out as it would go behind it. With LCDs today, it's continuously illuminated, but if you take a slow motion video of it, you will still see them changing as they go down the line. And this is actually limited in modern systems at modern resolutions by the bandwidth of our cables that we wind up pushing across them. They limit how fast you can refresh the screen, how fast you can push the pixels out. So if you total all of this up, this is how you get to this 100 milliseconds of time for a typical console game, and then you could have another 100 milliseconds from this sensor kind of just being poorly configured at the beginning. The challenge then is to say, how do we get this responsiveness down to 20 milliseconds? So basically cut it by an order of magnitude from a bad case to what we want in our good case. So the typical kind of discrete way you could look at it is say, well, what could we do in each section of this to make it better? You can put in the hard GPU sync there so that it doesn't buffer up too much. You could disable triple buffering to cut one frame off of that. You could just say, well, we're going to do a simpler game that doesn't need this pipelining, so it can be just one frame. And you say, well, if you also make the graphics simpler, if you're doing a game that was 5 years old or something that doesn't need the power of a modern system, then you can jam those together. You can have the CPU rendering to the graphics processor in one frame. But it seems really harsh when you start looking at, if it takes 16 milliseconds just to scan out the screen, how do you get to 20 milliseconds for the bottom of your screen at least, where that seems to imply you've only got 4 milliseconds to do everything else? And so this is where you start trying to find creative ways to cheat, to find out ways to bypass these things and still accomplish your goal without necessarily going through everything the conventional way. And most of what's been possible for virtual reality systems is bypassing sensor inputs much later. So we have this long pipeline that you want to go through. Some of the key tricks are figuring out how to bring updated sensor information in after all of this and still get mostly what you want. And now, as with all really good engineering trades, it is a trade, it's a compromise. You're doing something that is not perfect. It is not as good as if we just had a computer that was 10 times faster, we would just be able to do exactly what we've got, and we'd get in the realm that we want in our responsiveness, and life would be wonderful. But when you can't wait around for computers to just get 10 times faster, sometimes you need to figure out how to make the really smart trade-offs. And when you looked at the kind of the value curves there, you can say, there's a really steep value curve here. I really want to I'm willing to sacrifice some things to bring this value curve up from this low area up to this high area. I maybe don't care as much about that final tail off at the top, but it's really valuable to kind of get up there. And you can have kind of bitter arguments about priorities when it comes down to things like this, because for anything that you want to cut, you'll be able to find somebody that thinks it's the most critical, important piece of the project, and it's just, anything but that. But so the path to cleaning this up for virtual reality was, the most obvious thing was fixing the microcontroller where it was doing all of this filtering to make its body frame stuff. And this is where I took my aerospace code and said, forget the body frame stuff, give me the raw sensor values. And talking to the company and saying, well, this 125 hertz update, that's okay for most things, but can you do better? And they just said, sure, 250 is easy, maybe 500. Sometimes it is. If you take it as a given, if you take it as just you're the software guy writing the computer code here, your peripherals are just what's given to you. But sometimes it's trivial for a peripheral vendor to be able to say, oh, I didn't know that was important. I'm just changing one character in a configuration file, and I can give you double the update rate there. So it's like you can pick up, so then that 8 milliseconds gets cut in half to 4. All the filtering in there basically goes away. So that's still looking at, okay, maybe all told you're at 6 milliseconds or something kind of coming into the sensor when it gets into the PC. So you still don't see how all the rest of that stuff crushes down. One of the other major tricks, hard to do on the PC, but like on the mobile systems that we do, is For decades now, people are used to this presenting an image to the graphics system. You say, I've finished my frame, pass it on to the video display, start scanning it out. But in the old days, graphics programmers would do what we called racing the beam, where the screen is scanning out in this way. And if you know what you're doing, if you know where the raster is in memory, you can be drawing things kind of right ahead of it. So it's possible to actually get a millisecond response time if you know exactly where it's reading from memory and you are very carefully rendering right ahead of it. So conventionally now, like in mobile, our screens are actually, they scan sideways. Your phone, it's considered a portrait display rather than a screen that scans in landscape mode. It scans from left to right like this. So we split it into two pieces, and you've got the two different views. And we make sure we draw this view while it's scanning this one out, and vice versa. So now you don't have 16 milliseconds, you've got 8 milliseconds there. That's a big cut off of it. But you still look at your game and say, even with a simple game, this is going to be 16-something milliseconds, even if you're doing all of the computing and all the graphics inside one frame. The next trick was to do a reprojection, and this is where you're coming into some of the actual compromises. When you've rendered an image, it's a perspective image from one point of view. What you'd like to be able to do is say, I just spent 40 milliseconds from the time I rendered the input to generate this image. I've got an image, it's perfect, but it's perfect for the time 40 milliseconds ago. Instead, you can take that image and say, well, I can look at the sensor again now. Instead of just reading the sensor at the beginning, let's arrange to read the sensor like right down here, a couple milliseconds before you would be ready to scan it out. And you get that information back and it says, well, actually, we're pointing this way. You know, you started off pointing this way, and maybe you predicted and you guessed that we'd be over here, but actually we're over here. Given that information, it's possible to take your whatever nice picture you've rendered here and distort it and warp it in a degree where if you know that I should have been looking a little bit more that way, so you move it over and its perspective distorted a little bit that way. It's not perfect, where if you really moved a lot and you guessed really badly, you might not have anything over here. It might just be black because you want to limit how much you render. Maybe you render a little bit more if you've got a lot of graphics power. You could guess, you try to make the best guess you can, but you fix it up here at this late time. And this is what I'd been calling time warp, where at the very end we arrange to, after we've drawn everything, read the sensors again and figure out how to distort the image that we actually drew. So at this point, it's possible to be here under 20 milliseconds. Like on our mobile systems, we're usually around 16, 18 milliseconds, depending on various things. We cut the inputs a couple milliseconds, scheduling's a couple milliseconds, a few milliseconds for drawing it on the time warp, and then 8 milliseconds for scanning out, plus a little bit of cushion. The trade-off, though, is that this might not always be perfect, and in fact, it's very close. The perspective math works out so that some part of the image that you're looking at here can be almost pixel perfect for something that is an orientation change only. But in virtual reality, if you've got a positional change or there's animation going on, that won't be exactly correct. And we had bitter arguments internally about how important some of this was in the early days. But the ability to get that responsiveness down to a fairly important point of this 20 millisecond range was really worthwhile to make these trade-offs. But it's then interesting to say, what's you call the speed of light possibility here? How low can you get this in the kind of the best case? And there's things that we do that we've looked at, like instead of taking the screen and splitting it into 2 pieces, what if we split it into 8 pieces and schedule it just before each one? You could then knock an 8 millisecond delay down to 2 milliseconds, cut 6 off. This comes back to kind of these benefit curves. I look at it where you've got very, very bad value there. It climbs really steeply, and then it climbs very gently, if at all. And so kind of feel we're at this point where we can make experimental studies and set up a system and get it down to be very close here, and it doesn't make a ton of difference. There's the possibility that with some things that like if we move to ray tracing systems where we can adjust the position as well. It might make more difference there. But right now, it feels like that's not a huge win. And that's where some of the real kind of engineering wisdom about all of this comes in, about figuring out how to fight like hell to climb up the steep part of that curve, and then knowing when it's not that important and when you can move on to dealing with other things. So this same basic pipeline applies in a more problematic way for hand controllers, where they have very similar capabilities. You've got an IMU in the hand controller, but it's going to have a wireless link going across it. So we're dealing with Bluetooth Low Energy as a transport protocol. Right there, like a Bluetooth stack can be half a megabyte of code. It's an extremely complicated specification, and there's lots of different ways that you could use it. And one of the bad ways it gets used is, again, if people are looking at this from a specialist standpoint, you say, I'm going to do the best job possible filtering this IMU. It's going to be the cleanest data, but I'm just going to use a stream abstraction to talk to the CPU. And you'll find a nice little library. It's like, here's how to do the equivalent of TCP over Bluetooth, and it will just buffer it up and chop it into the necessary little transport packets and generally be a horrible situation. So there's opportunities to be really broken there. And then when you get to all of this, you have to go through the same things, but the same time warp trip can't be done for the hand controller because the hand controller is baked into the rest of the screen. You can't just move that little piece of it. You know how your head is moved. You can consider doing more tricks then, and this gets into hairier trade-offs where you can say, well, what if instead of rendering your hand into the main scene, we render the hand to a whole separate layer? It's an image all by itself. Then we could do time warp tricks. We could move it around that. But then you have to worry about cases of, well, what happens when you put your hand behind something in the world? If you're just layering it on top, then that's not going to work. And you say, well, do we carry a depth buffer for it also and make our compositor do depth comparisons as we put it together? And it starts getting to be, a big mess. There's a few tricks that you can do, like late latching. You can't go all the way to the end and do a time warp, but there are ways that you can set up so at least that the GPU figures it out right here, and it might have 14 milliseconds more latency than your head, but it can still be a lot better. But luckily, the hand feedback, it's important to get a sense of where your hand is, but it's not as important as your head. It's kind of like going down the threshold to a mouse and to a joypad, where a hand controller is somewhere in that neighborhood rather than the exact responsiveness that your head expects. I mean, your brain, your eyes are right there. Your brain expects when you look over, the world is going to be a certain way. When you're moving your hand around, it's not as precise as people think it is. There's actually been some cool research done where people can make your hand, they will use virtual reality and put things on a table, make you reach for it, and you could be reaching like a foot further than your arm actually goes, but if they're drawing it correctly and you're looking at it, you can fool yourself. And I mean, I had this done to me at it was like Texas A&M. They had something set up, and you're reaching for something, and they're moving it around a lot as you're looking around, but it's not as critical as your head. While if you pitch your head 5 degrees off, it will be immediately noticeable and will make you uncomfortable fairly quickly. So another one of the things that I'm working on right now is the end-to-end system problem of virtual reality video, where this is one of the most important uses for things right now. But largely, I think the quality that most people see when they see a 360 video or stereo VR video is pretty bad. We had one of the things that I was really happy with when we first launched the Gear VR product. We were able to include a 16 gigabyte SD card with it, so we included some pretty high quality footage with it. But since then, all of them have just been everybody sees streamed video, and only a small fraction of the people will go to the trouble of downloading high-quality video. And this pains me deeply when I'm, knowing that people are seeing these very low-quality video systems, and a lot of them you won't even be able to see the 60 frames per second stereo where it really becomes kind of magical and you get to see the value from it. But it's a hard problem because there are, even the best case, the side-loaded stuff that we had, isn't at the quality level that we would like to have from it. So this is, again, going back to these speed of light notions. I start by saying, what would be the best possible quality that we could deliver? And the way we can test that is if we say, all right, we've got, say, this phone that has 1440 resolution display. Even video encoding and decoding, that's going to have quality losses of some level, but we can at least make small test cases where you've got a phone with 4 gigs of memory or something, just load up 4 gigs of frames and switch between them, 60 frames per second, perfect, no artifacts, and you can look at that and say, oh, this is just spectacularly good. This is so much better than what people are actually seeing. And that's where I kind of define opportunity as an engineer, when you can tell that the difference between what's possible and what you're given and what people are seeing today, the delta there is the opportunity that you have for improving things. So if you look at this entire pipeline, this is an even longer pipeline than the input because it crosses people and organizations and the internet as it's going through here, where you have the way the content is created on one side. At one end, you've got a camera. A camera generates a video file. The video file goes into some kind of post-production thing to warp it from, say it starts out as a fisheye, it's going to be warped into an equirect. So it does some kind of warping operation. It goes through whatever editing stuff they finally wind up putting it through. Then it goes into some kind of data compression system, and then it's put up on the internet. So internet server, people connect to that. It's streamed over various protocols. You have different versions for different bit rates. You stream over TCP with error correction. Eventually, over the internet, it gets down to somebody's VR system. And then inside there, we have that same route that we had before, where it comes in somehow as an input, it goes through processing, it goes through rendering, it winds up on the screen eventually. Now, the problem is the pixels that come out of the display there are so far different from what went into the camera. And this is where quality takes on a lot of different axes. We have, most people when they think about quality, we talk about quality in video, everybody thinks first about resolution. Oh, we got 4K or we're going to 8K or whatever, where resolution is kind of the buzzword. Same thing with cameras. And purists get really uptight about this, where they say you don't want to just look at the megapixels, you want to look at the sensor size, and there are all these other important factors there. But still, resolution is one of the things you'll look at. Then, a little bit more knowledge, you'll look at, well, what's the bit rate that I'm actually getting, coming across the internet. And people that have paid attention to video for a while, it's surprising how little we make do with now, where Blu-ray discs were going to be what was needed at the time for doing 1080p video, full HD video. And Blu-ray discs give you like 50 megabits a second coming off of them, and that's what video people thought was necessary to do a good 1080p video. Now, if you go stream 1080p video from Netflix or YouTube, you're getting a couple megabits. Now, our compression's a little bit better, but it's not that much better than what we had then. So really, we're already used to settling a lot on video quality. VR makes it much worse because when you're looking at your cell phone, you're looking down there, little compression artifacts and little losses of quality just don't make that much difference. But when it's blown up so that one pixel is occupying 1/10 of a degree or so of visual arc, those are pixels that mean something. It's kind of like in the old video game days when we had 320 by 200 resolution. We talked about bathroom tile-sized pixels, where a pixel out of place really meant something. A crack between triangles was something that just kind of sat there right on your monitor rather than being something that just gets lost in the anti-aliasing system. But video resolution is something that interesting things are happening, where for a while there was the arms race with the phone manufacturers, more and more resolution. We got to the point where like all the phones that we do VR on are 1440 resolution. And one company, Sony, went and shipped a 4K phone, and it turned out nobody cared. And in fact, it's turned out that even Samsung, who has pushed all of our nice 1440 phones, modern Samsung phones have an option to actually run everything as if it was only a 1080p phone, because it turns out most users prefer the savings in battery life and thermal overhead for the 1440, because a lot of people just literally can't tell the difference. So it saddened me greatly to find that we're not going to be getting lots of 4K phones for VR, because that would have been great to kind of get that for free, but probably not happening. And really, more resolution on the display device wouldn't help the video problem at all, because the videos are coming in at much lower resolution already. The things that can help it are, obviously, if we can get more bit rate. So then you say, well, look at our transport stuff. And I've profiled some of our transport and found that in many cases, we're not getting anywhere near what you should be. Like if you do a speed test and you say, I'm getting 20 megabits per second transfer. But then you look at what is your video streaming actually delivering. And you're like, well, this is only half of that. Why can't I get more, get a better bit rate, just choose a better representation? So that's one direction to go at. But that's a rabbit hole all by itself. What determines the streaming? For instance, at Oculus, we use the ExoPlayer project from Google, which is a big project, which is layered on top of lower level video codecs. It has lots of plugin systems and all sorts of things that go on in there. So what I've done to start addressing that is I started from the lowest level that I had access to as a user level programmer on Android. And I wrote what I've been calling video direct to say, if I look at only the pieces that deal with the decoding, these hardware interfaces, what if I just feed them myself? Let's take out this couple 100,000 lines of code that maybe I could dig through and figure out how to optimize, but carve it all away and start kind of from the bedrock. And of course, it's not really bedrock. That's a driver interface that goes down to things which talk to hardware below that, which has tons of firmware in there. So bedrock for an application programmer is really still the top of a tall stack of things that happen at the operating system and device driver level. But still, it's one of those things that a lot of important things can happen. One of the things that had bugged me for years since we started on this in virtual reality comes down to another tempo issue, where I had pointed out how we've got these 60 frames per second hard switches. If you look at this, and this will probably bug a lot of you forever after, because once you've seen it, you can't stop seeing it. You can't unsee tempo problems in digital video, but they're all over the place, where if you get especially a 60 frames per second video, something that should be going perfectly smooth, it is shocking how many display devices will wind up having stutters and hitches in them. And there's a lot of reasons that can cause this, but it's a matter of video has timestamps in it, and it says this number of microseconds here, this number of microseconds here. But the actual display that's coming out is at slightly different times. Now, it used to be in the old days, TVs, they really were 59.995. They were very close to that. But all the digital systems can drift more than you might think. Our phone displays are often 59.2 frames per second, 60.1. In the best case, this would lead to smooth, 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 and then once every second or two, you would glitch one frame, either because you had to drop one or you held one frame for 2 frame time periods. But unfortunately, the way a lot of these systems are written with buffering and different timestamps, there are cues, you get into beat frequency problems where you have things that are coming out at this almost regular interval and this almost regular interval here, and we wind up with cases where when I graph what should be a nice sawtooth where it's going up like the latency on here and then drop down and then go up. I'm like, okay, I don't love that every second or two it's got a little correction, but instead we wind up with things that look like, and there are a lot of systems that wind up doing this. I was shocked at this year's Game Developer Awards. They had this many $million display system back behind all the presenters, and they have nice animated graphics going on, and I'm watching it do that same damn thing. Smooth, judder, 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 smooth, judder, judder, judder. And you see this in a bunch of other things like TV sets that are trying to do frame interpolation, like your TV that wants to be a 240 hertz television set. So it takes the frames in and tries to fabricate, you can actually call it detail hallucination, to build in frames that weren't there. And there's neat technology behind that. But they often wind up having tempo problems here as they have to switch in and out of being able to do that. So one of the goals, and this had been bugging me for a couple years, but as I started digging into this long pipeline, and I'm still tearing this apart literally, like yesterday, this is one of the things that I'm working on, but there are things to be trimmed in all areas of this. But the first part on the video playback, taking it, instead of just saying, video player, play this bunch of data that I'm pushing at you, taking control at the frame level and saying, all right, decode this frame, it's a frame, don't do anything with it yet, I will control when it goes out. So I wanted to fix this perfectly because I wanted it to be a straight line where just every frame has exactly the same latency. And I could do that initially, where you take a frame, and I say, I'm ignoring the timestamp. I'm just going to take the next frame. I'm going to release it on the next frame. So it's always going to be one video frame gets one media frame. It's going to be perfectly smooth. The problem is the audio drifts out of sync, because the audio is on this true time, and it's going off through this other completely separate thing. And audio systems have their own equivalent set of buffers, where it goes through 3 different mixers before it finally makes its way outside that. So what you have to do to get to this perfectly flat line instead of the messes there is go 1 for 1 on video, or 1 for 2 and 30, or 3 for 2 on 24. And also take the audio, and you have to slightly resample all of the audio by 0.5% or something, so that instead of being at exactly 44.1 or 48 kilohertz, it's going to be 1% off. And musicians there are probably some musicians that will wind up hearing this and say, hey, you're some fraction of a semitone off on your musical representation. But it turns out, for most people, it winds up working great. And I can have this smooth as glass video playback with the audio synced up to it, and even do a better job getting the lip sync right than the standard system things do. So I've taken kind of this part of it here from the playback part and fixed a bunch of things. And this is working well. But it's still not at all the quality that I want. I've got the network interface side of things, where I think that there's a factor of at least 50% by just optimizing that a lot better. Interestingly, one of the directions that we've taken for the last year plus, and I was really big on this at the beginning, it was this notion of view-dependent transforms, where video streaming, the whole idea that normally sending a whole 360-degree view when you just spend most of your time looking forward, that seems just such a huge waste. It's like you're looking at one face of a cube, and you really are only seeing 1/6. And even if you gave yourself a lot of slop, it felt like there was a factor of 4 in quality to be gotten there. So we implemented all of this, and the high-end videos it builds like 20 different versions, and it picks the best one as you're looking at it. But if you whip your head around, you're seeing this very blurry version. And if it fixed itself really quick, that'd be great. But sometimes you can be there looking for a couple seconds before it corrects. And it's a little debatable whether that's been a great trade-off. Now, part of that is it comes down to the same types of things with tempos and trade-offs, where these aren't 16 millisecond blocks, but in video compression, you deal with what are called groups of pictures, or GOPs, where you might notice that unlike like an old analog system where you could theoretically go to any frame in a video, most digital video, there are discrete places where you can immediately sync to. Because it's set up, the way video compression works is you send over one good independent frame, and then the other frames reference that frame. So you can't just jump into the middle because you need what it's referencing. That's how you get 100-to-1 compression instead of 10-to-1 that you get out of still images. So you've got this problem of video is chunked up into these GOPs, and the horrible trade-off is the bigger the GOPs, the better your compression. So if you say, well, I really want to get this down to very low bandwidth, then you want to have large GOPs, lots of delta frames, very few kind of intra frames. But that then fights with this idea of being able to switch directly between the different viewpoints, because you've got say you picked 5 seconds, you've got a great compression ratio, but then you turn around, it could be 5 seconds, best case, for it to come in. And because you've got these same input problems, it could be even worse. It's so easy to slip past the edge and have it wind up being 10 seconds for some reason. So instead, you pick a small number like 1 second, but then you have relatively poor compression. And it's this trade-off of, well, I'm getting 4 times better resolution in theory ahead of me, but my compression has gone down 30%, and it's not that great on the backside. And part of this is that the system, and internally, like we started off building a custom server that was going to be the minimum response time, and for various reasons, it wound up shipping on something that is more or less a stock server using stock MPEG dash protocols. And I still, in the back of my mind, think that we abandoned that too soon, that we've got this, again, hundreds of thousands of lines of software code that are not doing exactly what we want. And I want to carve all that away and build the raw server again and see if we can make it switch in the minimum amount of time. But if we can't, there's still like other things that we can do to make it work out better. Where if you go further up the space, all of the video productions right now in VR, they start with conventional cameras, maybe with wide-angle fisheye lenses, and then they're deformed into a projection, usually what's called an equirectangular projection, which is kind of your Mercator projection sort of thing. There you can argue about projection efficiency in a lot of different ways, about how you've got wasted pixels up at the poles, but that's kind of the industry standard. We use cube maps for some things, but they have different trade-offs. But an interesting thing, or an important thing, is that anytime you do an operation on an image, you're doing damage to it. I mean, people in electrical engineers might talk about signal processing and the Nyquist limit, and in theory, you can recover any signal from any of that, but it's not really true in reality. Every time you resample an image, especially if you wind up compressing it at the end, you are damaging the image irreparably. So every time you change the shape of something, you are throwing away some quality. Now, it's not as dominant as as like what bit rate you might be at, but it does matter. And this has been something that I've been very proud of in just the last couple months. We got to fix one of these second-order effects, like avoiding double resampling of our user interface text and getting it into the right color space. And these are, they're second order. They're not as important as getting the resolution right, but they are helpful. And there's a bunch of these in the video pipeline. So one of the things that I'm working on this week is setting it up so in some cases you can take what comes out of the camera, which is a fisheye lens, which has kind of radial distortion where it's got a center. And you look at it and it's a horribly distorted image, but rather than in pre-processing turning that into one of the equirect images, it's ruled like that, which takes a lot of distortion, taking this image directly, compressing it, and moving it directly to the end, and putting some smarts on the end there so that it's a graphics processor. It can pretty much exactly as easily take something directly from a fisheye projection as it can from an equirect projection. And that allows us to get rid of at least one, if not more than one projection there. And then you start getting into some really interesting details where the way you've got separate cameras here. If you want to make a stereo video system, you're going to have at least two views, a view from each camera. So you want your picture to wind up looking like fisheye view here, fisheye view here. And again, it's interesting where that will look vaguely similar to what the VR view comes out of, but they are different distortions. And of course, the VR view could be looking at any part of what these fisheye views are. But even if you say, all right, I want to take the fisheye data directly from this camera and move it here, there's things you can do that will mess it up even just in that transformation. For one thing, your camera's probably putting out H.264 video compression, hopefully at a pretty generous rate. Your camera might be putting it out at 40 or 50 megabits per second, which you still get compression artifacts in it, especially if things are moving. But that's a far cry from what might be 5 or 10 megabits per second on the final part there. But even there, if you take the image and you've got this fisheye centered in a normal camera frame, you just say, well, I want to grab this part and I want to move it over here, take the other camera, grab it and move it over there. Digging down about what actually happens, the way compression, both video and still image compression works is by chopping the image up into blocks, usually like 8 or 16 pixels. And you've all seen poorly compressed images where you can literally see these blocks, blurry blocks with sharp edges between them. So you've got a problem where if you say, I want to take from, pixel 511 to 1,712, I'm just going to chop that out and put it here. Picking a number like 511, that's going to be slicing one of those given blocks, taking it apart, recompressing it. You have to decompress it to crop it, and then recompress it down, and you're spreading the damage that's happened in the compression across multiple blocks. So I'm looking to try to get this, again, the speed of light. What would be the best possible thing that I could get here would be taking the output from the camera, ideally not even decompressing it. You could take two cameras and take the two camera streams, and it would waste more, but to find out what the peak quality would be, potentially decode two complete camera streams, so the pixels that come from the sensor there make it all the way, and you just do one bilinear interpolation on the end. But even that is hiding things. So this is this onion of layers upon layers of things that go on. If you look at, like with a magnifying glass, a video screen, Normally, like a desktop monitor, you'll see it's broken up into triads, usually laid out like that, where you'll have a red pixel, a green pixel, and a blue pixel. And this is, when you hear a monitor called like a 1920 by 1080, it's actually 1920 times 3 horizontal resolution. And this is sometimes used for tricks to make text rendering look better, and this is exploited in some ways. The phones that we use, and in fact the OLED displays in the PC headsets as well, they actually cheat on this, and this is something that a lot of people just hated this in the industry, but the OLED displays use what's called a pentile layout, where they have twice as many greens, where usually they've got like a checkerboard pattern like this, where you might have this many greens, but then you would have reds and blues at half the rate. So at the hardware level, behind your back, as a programmer, you say, I've worked really hard with the graphics processor, and I've rendered this perfect image that's RGB, and I've got a million reds, a million greens, and a million blues. The display is actually taking those million reds and just mashing them together into 500,000 actual display pixels, which is unfortunate. On the high-end PC systems, at the firmware level, we can go in and take it out of that mode and take better control of directly putting it in. But on the other side, all the way over here on the camera, cameras also have patterns that are very much like that. They're called Bayer patterns on the cameras. But if you again look at, under a microscope at what the camera sensors have, and of course the camera sensors, it's a similar thing where you might have a 12 megapixel camera. This is the difference between cameras and the displays. When a display talks about resolution, they're talking about full pixels, the full RGBs. When a camera talks about pixels, they're counting all of the subpixels. A 12 megapixel camera is 4,000 pixels by 3,000, well, not pixels, but sensors. And inside those, half of them are greens, same thing. And then a quarter, the reds and blues divide up the inside. If you take a raw camera image, then you're not going through any of the processing. You're reading out exactly what's in this sensor array. And if you have like a rainbow color image and you take a raw camera image and you display it as a grayscale, you can then pick out and see exactly what the pattern is. It's like, okay, these checkerboard are the greens at this offset, this other pattern is the reds, and these are the blues. So if we really wanted to get the best possible system, instead of having this image processor, like cameras and phones have this very powerful image processor system that tries to take this raw data, and they do crazy stuff with it to try to make bad photographers look better. They do all of this image balancing and sharpening and de-distortion, and the idea is not driven usually by a science of trying to make it a better sensor. It's usually driven by how can we make some magazine reviewers review of this phone camera look better. So people will do the side-by-side photos and they just say, well, does this look better? So they're doing crazy heuristic stuff in the image processor. You'd really like to be able to get just that raw image. In a video compression system, they don't take red, green, and blue. They convert it to YUV, which is an intensity color space because it's better for compression. So each of these, every change again, is destruction of data. So you wind up having, even before it gets out of the camera, it's been converted from RGB, Bayer patterns, into RGB, into YUV, and then compressed. So a whole bunch of things have happened already. In the best of all worlds, we would notice that, okay, this camera sensor has twice as many greens as reds and blue. Our display has twice as many greens as reds and blues. What we'd really like to do is hijack the video encoder there and say, forget this YUV conversion. Let's have you compress greens as the main plane and then subsampled reds and blues. Let's take this all the way through to the end and then have the display, knowing the offsets and these subtle things here that are different, go ahead and sample directly from that image. So this is one of my semi-long-term plans where looking at the entire system end to end, and these are all by different companies. I mean, in the number, there's 10 companies involved in this entire pipeline of things going through, but there's optimization potential to be had all throughout it. And I believe that the best case that we can get by wringing all of the fat out of this without changing any of the hardware at all I think that there's factors of several in the quality that we can deliver to the users. Now, it's always great that things get faster and we get higher resolutions. Well, we are hitting some of these limits where, all right, the phone displays probably are not going to 4K, let alone the 8 or 16K that we would like to have in some ways. We are running out of steam on kind of the Moore's Law free graphics power for things where we are settling now for a 30% boost each year in the power that we get out of these things, rather than saying that it's going to double every 18 months. Bandwidth's still going up at least a little bit, but there's hard fundamental things to be worried about with spectrum and how much we can possibly get out of 5G and different things. So these systems optimizations are still fertile ground for finding a lot of value. So I'm excited about this. This is one of my big kind of pushes for this year. The push on latency was the thing from a couple years ago. We have all sorts of other initiatives going on, but as you can tell, I'm still super excited to be an engineer and be working in all of this. We've already run over our time a little bit, but I've got time to take some questions. We've got a while till we get chased out of the room.
So yeah, we open this up for questions. Back here.
Yeah, you're talking about the kind of continual improvements that are happening from different companies. How do you guys kind of incorporate that into your workflow, like something like foveated rendering that would potentially add a huge savings to how much you have to get out of that GPU?
So like foveated rendering is for people that...
Make sure everybody kind of heard it.
So like how do we take in advances that might be happening from other companies? Like foveated rendering is the specific case of normally you've got a graphics screen, you draw the entire thing at a fixed quality level, but if you knew exactly where the user was looking, like if you knew he was looking over here, you could draw high resolution there and just let it fade out to much lower resolution across the rest of the system. Something that most people aren't aware of, the bandwidth of the optic nerve, like what comes out of your eyes, is actually a lot less than what your monitor or a VR headset has right now. The resolution that you have in your fovea, the very area that you focus on, is very high. They talk about retina resolution displays, and that does pretty much determine. You can argue about some of the vernier effects, but when you take a couple million pixel phone and you hold it at arm's length, that's about the limit of your visual acuity. But something over here that's still in your view, you've got over 180-degree field of view, but you've only got a couple degrees where you've got that acuity. And over here, things could be doing crazy things and you don't even notice. Like one of the examples I point out is I've got a dual 30-inch monitor system that I work on. And I can be looking at this and I can see the other monitor, but I can be waving my mouse cursor, which is like 256 pixels, and I can't find it. I actually have to go and look at it because in my field of view, 256 pixels could be changing and I'm not even noticing. So there's enormous potential upside for doing this and it becomes mandatory if we look at where we want to be with virtual reality, which really would be something like 16K displays, which we're just not going to get in the... It's interesting, you could fabricate a 16K display out of tiled silicon micro displays today, but it would be very difficult to drive it with anything like the quality that we do right now because most high-end graphics systems still wind up being pixel bound. But if you knew exactly where the user was looking, then you could say, all right, I'm going to render a lot right there and much less. And there's lots of different interesting schemes about exactly how you tell the graphics processor to do that. My pet scheme for foveated rendering, usually people talk about like rendering like one view here and a lower resolution view here. But if you look at like Wikipedia for like the foveal region, you'll see the graph is kind of a hyperbolic shape like this for the quality that you need in the middle versus the quality on the outside. And when I look at that, I think that looks kind of like hyperbolic asymptote. And there's a way you can get that with conventional rendering with perspective math, is if you wind up looking down like the corner of a cube. So you have basically cube rendering like this. You can get pretty similar fall-off shape to that, and you can back the view up a little bit. But there's a ton of this work going on in a lot of different companies about exactly how you wind up doing it. But the question of interacting with the other companies, like in Facebook Oculus's case, the standard behavior is to buy a company. And that's, it's, like it's almost an open secret in a lot of hot technical areas. If it's something that's really, on fire in the media and everybody's talking about it, the smart move is to get together with your friends, found a company, and, be acqui-hired rather than necessarily just putting in your resume. That's happened far more than I would care to. Like, we've had a hard time hiring computer vision people, and we've acqui-hired a few companies full of people that that work on that, and we've acquired an eye tracking company, and we have people working on it in research. I'm in a little bit of it, from my position, I've always just been happy to see whatever anybody makes, and it's exciting to work with whatever toys anybody can provide me as an engineer. It is, it's interesting being on the other side where, I have some things that I push for internally since we're actually building some displays and drivers and things like that, where I can say, well, it'd be great if we could change something here, it might work out. And it's a tough argument to have there because it's speculative when I can say, I think this will be a great idea. And it's one thing for me to just be tossing it over at another company, but internally in there, if somebody has to think, well, do we really want to devote resources to this? And it becomes the tough trade-offs, in that way. I do think foveated rendering we still have a lot of debate about the quality of eye tracking. There are systems right now that people can get demos of that do eye tracking and foveated rendering, and there are a lot of people that say they're just not good enough because of the same thing that I've been talking about here, the stacked up latency, where if you go through the latency, the way these eye trackers work is they're cameras. They're cameras that basically look at the eye, and they go through a computer vision processing step, and this stacks up to a whole lot of latency there before you even get a value out of the sensor that can be put to the system where you might be choosing to re-render it in different places. So we come down to possible ways to bring it in as late as possible into the graphics processor, ways to push things around in different ways. And I think that I feel pretty good about it. I don't think that's one of the deep unsolvable problems of our industry. And in fact, there's the push that's valuable right now with foveated rendering is, even without eye tracking, it's helpful to do some kind of foveated rendering just because the lenses in the head-mounted display fundamentally distort the view. So you have more detail in the center and it's blurrier on the outside for just the way the optics trace out. So if you have low overhead, it makes sense even today to render a foveated view and then a blurrier outside view. But this is one of those engineering things that becomes a tough trade-off, because if you have a high overhead driver interface, you'll spend more time doing a second rendering pass for that than you'll actually save, because you can save on the pixel side, on the fragment side, but you can spend more on the CPU. And depending on your system, you might be bound one way or the other. Yeah.
Another question?
Yeah.
I have minimal nystagmus, which means involuntary eye movement, and I'm really excited about VR. I got to try a few of the devices recently, and they're really neat. But I'm wondering, what does the future of VR look like for people with low vision or involuntary eye movement? Will it be like accessibility features, or?
So this is one of the. Yeah, so the question is accessibility features and people for various visual impairments. So there's some, I think, let's see, there's a paper.
You wear glasses.
Yes. So, and in fact, like some of the ones, the Gear VR has a focus knob where I can wear without glasses and adjust the focus enough, or I can just jam it on over my glasses somewhat uncomfortably. There are possibilities that are being investigated with varifocal to be able to do displays in some cases for people that have different some eye problems. Now, people, when they hear that we do what's called distortion correction to correct for the lenses, people think immediately that can we use that to correct for eyeglasses, and unfortunately not directly. The distortion correction that we do in head-mounted displays now is spatial distortion, where most of the problems that people have that require glasses are focal distortions. But there is technology that's being worked on to dynamically adjust focus in different places, because that is one of the things that even if we had infinite resolution in the head-mounted displays today, you can tell the problem. Like, I remember doing the early work where I'd be looking at my desk in reality, and then there was a similar table in the virtual reality that I was looking at, and you take one off and the other, and you don't think about it consciously, but When you're looking at your desk here, everything down there goes out of focus because it's further away, while in VR they stay in the same crisp focus. And this is also one of the things that causes eye strain, where your brain normally does two things at the same time. It adjusts the focus and it verges your eyes to converge on stereo. In a head-mounted display, your eyes verge to the right place because you've got them drawn in two separate places, but the focus never changes. So that's something that doesn't cause the sick to your stomach feel, but that can give people a headache and cause some of the eye strain. So there's hope for some of the things with varifocal doing some of these possible corrections. And then there are some exotic display types that potentially could bypass other, some of the other optical things. Like for a long time, early on, I was excited about direct laser retinal projection, the idea of directly scanning lasers into your eye, because that's, yes, and I did build my own laser rig and put it on the lowest possible setting and very carefully peeked under, and when I did that, one of the manufacturers was like, "Don't do that, your eyes are too precious." But it was lowest power, and it didn't hurt myself. But the interesting thing about that is so many of the optical problems that people have that have to be corrected for with glasses and so on are matters of focus, where you have light coming in that covers your whole eye. It might be coming from a point in space, but it comes out, it covers the whole lens, and then the lens has to bend it back down to a sharp point on your retina to be read. With a laser, you scan over, the laser beam still gets bent by your lens, but it's fundamentally coming from sort of one point as it goes around there. And that has possibilities for being better for people. But even on just the simple level of people that just have really bad eyesight, that have very poor visual capability, one of the things that I'm kind of excited about is we just rolled out this major change to our kind of our home system and our web browser and these other things in VR. And one of the neat things is I fought this long, hard battle to get our user interface people to accept that putting things on flat surfaces is still the right thing to do, even in virtual reality, before everybody wanted to do crazy 3D stuff all over. But putting it on a surface is nice because it does mean we at least have that possibility of just moving closer to the surface, making it work better for people in some ways. But as far as like eyes jumping around, we still have debates about how important some things like eyes do what are called saccades, which are very quick jumps to different places. And I don't know if that's specifically related to the condition you're talking about, but there are theoretical discussions we have where the displays that we use in VR are low persistence, meaning that they're not continuously illuminated. Because if you take a normal, like if you take an iPhone and put it in a cardboard case and you do VR, it's terribly blurry because the LCD is on the whole time, and you look around and it's just smeared over the entire time between the frames. To make the crisp displays, we do basically the display flashes on briefly. And there's two ways that happens. Either a global shutter, and this has camera analogs too, because the same thing happens in cameras. You can have a global shutter where the entire thing is blasted at you at once, which seems to be the best. There's no distortions there. Or you can have a rolling shutter where they come on like the old CRTs, and then they're turned off some distance behind it. But a lot of people still think that there's some negative that's going to be happening there, where what if your eyes glance around, this eye is not seeing that? And I don't see that, and we still argue about whether it is an actual problem, but there's still kind of some reasonable debate. It definitely causes time distortion, so you have to, if you don't correct for it and you're looking side to side while it's scanning down, the whole world, we would call it waggling, because that 15 milliseconds, it takes that time to get down here. You look over, by the time it scans out, it should have been from 15 milliseconds over here. So it's like the whole world sheared. And if you're going back and forth, it's like the whole world is wagging like that. But you can correct for that with the same kind of time warp. You can say, not only am I believing that I'm looking here, but I believe at the end of this frame, I'm going to be looking slightly over here. So I'm going to distort the whole thing. Again, not perfect, but really pretty close.
So I'm going to ask one last question.
Okay.
And then if there's some people around that want to ask some things, maybe, I don't know if you can.
Yeah, I can hang around for a little while.
But of course, for the general public, everyone likes to know, why did you win the Emmy Awards? What was that for?
So there were two for, and there's an interesting little backstory for this where, so the Emmys, they had decided that they wanted to start honoring like game technology, and these are the technical Emmys, and it's for like user-generated.
Stage, did you?
No, don't do the red carpet things. But they were technical Emmys, and they're usually for things like people that have made advancements in the way the films work or the camera or the post-production things. And I got 2 for like user-generated content, enabling user-generated content and game engine technology. And so I had 2 of the great big Emmy statues, and they're massive, and they're like, I joke that the combination bludgeoning puncture weapon, because they're sharp on the end and they weigh like 10 pounds. But the funny thing was, like a year after that, there was a revolt amongst the film and television people that didn't want to be on the same footing as the video game people, and they downgraded those. And I got another one like a couple years later, and it was a little lucite thing like you'd get from somewhere else. But yeah, I've still got one of the big Emmys on the mantle.
Well, I'm really glad you're here today. I'm actually very glad that my wife wasn't here, because when she talks about latency, it's me sitting in the lazy boy chair, a cocktail, and how long is it take you to know VR, right?
Latency and all, and governs all of life.
And all kinds of things, you have to get the lazy boy down there and walk out and change clothes, right? So a little bit more than milliseconds. I think we should all give John a round of applause and thank him for his great talk. And I learned a lot today. Actually, I didn't tell you this, but I actually have a physics degree as well. So
Great.
This is all very interesting.